Okay, so remember the topic of this lecture, model checking. So we need models, first and foremost. Last lecture I introduced the model of transition systems. And what we have seen last time is that we have hardware circuits. And in particular, we have seen sequential hardware circuits. And we have seen program graphs. And program graphs are nothing else than a graphical notation to denote programs. And we can map both of them to transition systems. And why is this relevant? First, it shows that you can model quite a number of several, let's say, aspects like programs as well as hardware by means of transition systems. And secondly, what we will do in the rest of the lectures is that we're going to use this model, and that's the input model to the model checking. So this will be the input, so that will be the model, basically, of your system that we're going to put into this box that we're going to be familiar with much later, which is the model checking. Now, typically, a system is not just one single component. It's not just a simple hardware circuit or a simple program. Typically, you have a system consisting of many components. So what we would like to do is we would like to model that. So what I'm going to do today, as well as on Friday, I'm going to introduce several, let's say, ways in order to do, components. So basically, we would like to describe systems in a component-based manner. Component-based models, which basically, if you would like to see it as a diagram, you have several components. So maybe you have P1 up to Pn. In some way, these components, think about them as threads. They have their own behavior, but they also every now and then synchronize with other threads. And now the key point is there are different ways in which these threads can communicate with each other. And that's what we're going to study. So we are going to study different communication mechanisms. And some of these communication mechanisms we will see already today. So I will start very simple. I will start with the most simple way of doing multi-threading, means no communication. And we're going to see what that means on the level of transition systems as well as on the level of program graphs. That's the first thing I'm going to introduce. Then we're going to see what we call synchronous communication. What is synchronous communication? Well, I prefer to use the word handshaking. And that means that two threads or two components can communicate if both are in a certain state of their control and they both agree to communicate at that point. So they shake hands, so to speak. They do an action synchronously, and then they continue again autonomously. And the last thing that we're going to introduce on Friday is what we call channel systems. And the best way is to describe this as asynchronous communication. And asynchronous communication, in one sentence, you could summarize this as you have a mailbox. Somebody puts a message into this mailbox. It's not like with handshaking that you immediately have, synchronize. So once someone puts something in the mailbox, you receive it and you see what this other thread is communicating. No, there might be some delay in between. Somebody has put something in your mailbox, but it may take arbitrarily long before you get the message out of it. And the way we're going to do that is by means of channel systems. And then there is a fourth one, and that means actually full communication. That means, or full synchronization. Two threads can only, let's say, progress if they do everything together. So that's a kind of a full version of the synchronous communication. Good. So this all is about describing systems in such a way, P1 up to Pn. And the way we're going to define this formally is that we will have different parallel operators. So we will have different operators to glue those threads together. So I will start with an operator which is just written down as triple bar, like this. This will mean the no communication scenario. And each of those will then be a different operator on this level, on the language level, to basically, let's say, glue two transition systems together. Okay. So that's the plan of today and of Friday. And this is all under the heading of parallelism and communication. So the idea is that we have a, in quotes, real system that consists of many components, P1 up to Pn. And like in this scheme, we would like to provide a transition system for this thing. So what we would like to do is, if you give me a model of P1 up to Pn, I would like to be able to tell you what is the transition system. One single transition system that models all possible behaviors of the parallel composition of those n components. Yeah, that's the plan. So it's very similar to what we have seen here before, but it's a little bit more complicated because we're going to have these operations. Good. Now sometimes it's possible to have something like a parallel composition on this level, on the description, for instance, of programs. Think about P1 as a program graph, P2 as being a program graph. Then maybe we have some kind of a parallel operation on program graphs that glues program graphs together. And sometimes we have this on the transition system level. And even there, you sometimes have that you have one transition system parallel to another transition system, and so forth. Good. So the goal is to define these operations, these triple bars, double bars actually with parameters, as we're going to see. And that's what we're going to define. We're going to define this on transition systems, or if this is convenient, on program graphs. And the idea is that they model different kind of communication paradigms that we also see in real systems. Good. So the very first operation on my blackboard, which is now hidden somewhere here, it's the very simple one. You have threads. They run in parallel, and they never communicate. We call this interleaving. So interleaving takes concurrent independent actions of parallel processes. They don't interact. And what they do is you represent them by a non-deterministic choice. So the very simple principle is the following. Suppose I give you two very simple transition systems, one that has only two states, and this transition system can only do an alpha, some action. And then there is another thread, which is represented by this two-state transition system that can do a beta. Okay? It's not so relevant what this alpha and beta are exactly doing, but this is what we have. There is no communication, right? That's the principle. And now what we're going to see is that we would like to model the parallel execution of these two threads. And the modeling paradigm that we're going to use for this is known to be as what they call interleaving. What does interleaving means? Well, roughly speaking, you take all possible orderings of the actions of the individual threads. So either this one can do first the alpha, and then that one can proceed by doing the beta, or vice versa. The right thread is first doing the beta, and then the left thread is doing the alpha. This is also possible ordering. So what we're going to say is that all possible orderings are possible. So that means that if you take the parallel composition, and remember these triple bars means there is no synchronization, then this is going to mean that we have a transition system that has 2 times 2 is 4 states, and we have to model all possible orderings. And the possible orderings here is first blue, then green, or first green, then blue. Good. So this is the parallel execution of alpha and beta basically modeling on, if you want, two processors or two different machines. Whereas this models basically, this is a kind of a serial execution on a single machine. And now the idea is that we would like to adequately reflect the parallel composition of these blue and the green action. And the agreement is that we model this by means of this interleaving. Good. This quickly blows up, right? I mean, if there here would be two possible actions. So if you would have something like this, right? If you would have alpha 1, a state, alpha 2, a state, and you would do the parallel composition with beta over here, yeah, you would get all possible orderings. What would that mean? Well, it simply means that here is a transition system. Now, if you number the states, let's say this is A and this is B, this is C, and this is state 1 and this is state 2. What do you get? You get just the Cartesian product of the state space. So the initial state will be A1. Yeah. Now, what can happen? Now, either this beta can happen. That means we move to A2. Or alpha 1 can happen. That means we go to B1. What can happen there? Well, this state, we can still do the beta. Where are we moving if we do the beta? We move to B2. In this state, we can also do the alpha 1. Then we move here. And you see already the pattern, how this continues. And that state, we can still do the alpha 2. Yeah, because this one has only done the alpha 1. You can still do the alpha 2. Then you move to a state C1. And from here, you can also do a beta. And from here, you can do an alpha 2. And here, you end up in the state C2. Yeah? So it's really just the Cartesian product of the two transition systems. You model all possible orderings. Good, so how are we going to define this? This is defined as follows. We take as input two transition systems, T1 and T2. And now what we're going to do is we're going to define this Cartesian product, which means that the set of states is just a Cartesian product of the state space of the individual transition systems. We take the union of the actions. What are the initial states? The initial states are just a Cartesian product of the initial states in the first transition system times the initial states in the second transition system. And we have a transition relation here. And this transition relation is given as follows. And this follows the same, let's say, pattern as we have seen in the previous lecture. Remember that we have those rules that say, okay, there is a premise. And if the premise holds, then we can draw the conclusion. So the two rules that we have here, and the rules are symmetric, is that, okay, if S1 can move by alpha to S1 prime according to the transition relation of the first transition system, then a pair of states S1, S2 can also do this alpha under the transition relation of the parallel composition. And what will be the resulting state? The resulting state will be that S1 has moved to S1 prime, which is written in the premise. And actually the second thread did not do anything. It simply stays in S2. So this state, the second component, stays in S2. Yeah. The rule on the right is the symmetric version of the rule on the left. This simply tells you that if S2 can do an alpha according to its transition relation, so that's the transition relation in the second transition system, and moves to S2 prime, then the pair S1, S2 moves according to alpha to S1, S2 prime. Yeah, so here's the reverse. S2 moves, but S1 stays in S1. Good. The last two components that I have to define is the set of atomic propositions, and the atomic propositions is the disjoint union. And how are we going to define the labeling? Remember, the labeling of a state is the attachment of, let's say, the most elementary properties to states. And what we do is we simply say the labeling of a pair S1, S2 is simply the union of the labelings of S1 in transition system 1 plus the labeling of that state in transition system 2. Good. Okay, this I already explained. So formally, what is written down here is actually that the relation that we define by means of these two rules formally means that we define this transition relation as the smallest relation satisfying two rules. Dot 1 is corresponding to the one on the left. If the premise holds, then the conclusion holds, and the same for number 2. What is important on this slide is the word smallest relation. Yeah? Only those things that really satisfy these two rules, those are the rules, those are the transitions that you can include, but nothing else. Good. So here is a very simple example. It's called useless lights for a non-crossing street. So suppose we have just two streets, we have two traffic lights. The two traffic lights are very simple. So light 1 has just two states, red and green. It can move via action alpha 1 to green, and it can move via action beta 1 back. And similarly, we have light 2. So what's the parallel composition? The parallel composition of light 1 and light 2, according to this operation, which means no synchronization, is just what we have defined on the previous slide. And that means that provided that we have a pair, let's say for instance green, red, what are the possible transitions in that state? No, that means that this light is in that state, that light is in that state, green and red. What are the possibilities? This one can move with beta 1 to red, and that means that this state can also do a beta 1, right? This corresponds to this transition, where this component from green moves to red, whereas the second component stays in red. Similarly, you see that in that state red, we can do an alpha 2. That means that in the state green-red, we can also do an alpha 2, and that corresponds to this outgoing edge. And what we see here is that the first component stays in green, green, green. The second component changes from red to green according to this transition over here. Good. So now let's look at what happens in terms of programs. So here we have two actions, one that doubles x and one that increments x by 1. So in terms of a transition system, this would look as follows. We have here, suppose we have a state where x equals 3. Then if we perform alpha, we double x. If we perform beta, in that state, we just increment x by 1. So in terms of interleaving, this would then be the following. If we would apply the same principle as we have done on the previous slides, we build the interleaving of those two transition systems, same principle as before. So we start in the state that corresponds to the pair of states of this state and that state, which correspond to the state x equals 3 and x equals 3. Now two possibilities are possible, right? Either alpha appears, which means you double the first x, this x is not changing, or you increment the second x, this corresponds to that state, and after doing first the alpha, you can do the beta, you end up in this state, and doing this, you end up in that state. Good. So this is a bit strange, because if x is a global, let's say, shared variable between the two threads, then we see that we get inconsistent states. If x would be a shared variable, then x cannot be 3 and 4 or 3 and 6 at the same time. So this shows actually that the interleaving operation on transition systems for these kind of programs that share variables does not work. Yeah? So instead, what we are going to do is we're going to interleave on program graphs. Yeah? So what I'm saying here is the following. Suppose we have two program graphs. PG1 and PG2. They have some shared variables, x, y, whatever. I would like to give an adequate representation of the multi-threaded, let's say, composition of these two program graphs. So what we are going to do is I'm going to define an operation on the level of program graphs. Right? This will give you a program graph. One program graph, namely the modeling all possible behaviors of, let's say, the two program graphs. And then what we can do, we can apply the mapping that we have seen in the previous lecture. because in the previous lecture we have seen every program graph can be adequately represented by a transition system. So now we map this by means of this mapping to a transition system of this program graph. Yeah? This is the trajectory we're going to take. What the previous slide is showing, well, what we also could have done, well, maybe this is also, we can define this also as a kind of a program graph, as a transition system. So we could have built a transition system of PG1 parallel to PG2, right? And we're going to see that those two things will differ. It's not the same thing. Okay, so what we are going to do now, rather than doing the transition system level parallel composition, I'm going to go one level up basically. I'm going to do this on the level of program graphs. So I give you two program graphs, a blue one and a red one on the right, or purple is it? And we're going to see the interleaving operation of P1 and P2. Same principle, we're going to take the Cartesian product, but not the Cartesian product of the transition systems, we're going to take the Cartesian product of the program graphs. Okay? So what's the idea here? The idea is that we're going to take as the set of locations the pairs of locations of the first program graph and the second program graph. And we have to have edges. And remember what were the edges in the program graphs? They have guards and actions. So this means if the left program graph number 1, has an edge from L1 to L1 prime, guarded with guard G, and doing action alpha while evolving, then actually the pair L1, L2 can also do G alpha, where L1 evolves to L1 prime according to the premise, and L2 stays where it was, it stays at L2. The rule on the right is a symmetric version, so this simply tells you that if L2 evolves into L2 prime, then the pair L1, L2 can do G alpha and goes to L1, L2 prime. Okay? So it's the same principle as we have seen previously, but the important difference is we do it now on the program graph and not on the transition system. Good, so let's do an example. Same example as before. We have one thread that wants to double x, one thread that wants to increment x by 1. Right, so now they are represented as program graphs, not as transition systems. So this is a program graph that can move from L1 to L1 prime by doing this assignment. And remember, if the guard is true, we omit the guard. So actually what is written down here is true, semicolon, x becomes 2 times x. And the same over here. X is incremented by 1. Good. Now, according to the same principle as we had before, we get the following program graph, which is just a Cartesian product. So L1, L2, you can either double x or increment x by 1. Suppose we go to the right, then we increment x by 1. That means that we are in L2 prime. This program has finished, so the only thing we are left to do is double x, and that gives you to this location. Okay? So this, what we have seen, is we go from the parallel composition of 2 program graphs to a single program graph. Now let's see whether we still have this inconsistency issue which was happened before. So now what I'm going to show you, now the transition system of the transition system of this program graph. So I take the program graph which is on the left bottom of my slide. And what we're going to do is we're going to apply the mapping that we have seen in the previous lecture. What is the transition system underlying this program graph? Now remember, the states in those transition systems were pairs of locations of this program graph. Now here we have pairs of locations. So these are these L1, L2, plus the variable valuation. And like in my previous example, I just assume, for the sake of example, that x equals 3 initially. Good, so what can happen then? Well, either we can move to the left, right? That means we evolve to the location L1 prime L2, that corresponds to those 2 components, and we double x, which means x equals 6. Then we perform x becomes x plus 1, which means we go from this state to that state where you have seen that L2 evolves into the location L prime 2 and x is incremented by 1. If, however, we move here and then we move there, then it's clear we first increment x by 1, 3 plus 1 equals 4, then we double x and we get 8. And now we get exactly, well, what you expected, namely, depending on the ordering, you first double x and then increment x, or you first increment x and then double x, you get two different outcomes. And this is now adequately represented by this transition system on the right. So this is the procedure we're doing. We have this operation that tells you what is the parallel execution of two program graphs. This gives you basically the Cartesian product. And on that, we apply the mapping of the transition system, and this is the transition system that actually adequately represents the parallel composition. And we have seen in the previous example that this one is not, and in general, these two things are not the same. Yeah? In absence of shared variables, this is not a problem, then they are the same. But as soon as you have shared variables, this is no longer, it's no longer the case that the two different, let's say, trajectories yield the same transition system. So you can view shared variables as a kind of communication. It's not a real communication, but of course it's a kind of a common variable to all threads. And one can read this variable, the other thread can write this variable, so it's a way of communicating, in some sense, values between threads. Okay, so that's what I just explained. The transition system of P1 parallel P2 is not necessarily the same, so this one is not necessarily the same as the one that we have just seen here. Good, so let's look at an example. And this is an example that we are going to see quite often, I think, along these lectures. We have two processes. And these processes have access to some shared variables. Think about a bank account. And now what we would like to control, we would like to control that basically a kind of mutual exclusion that only at most one thread at the same time can read these variables. So the typical way that you have been acquainted with are things like semaphores. So semaphore Y in this setting is a binary semaphore, which means it has the values either 0 or 1. So think about a program that looks as follows. So typically a thread is an infinite loop. Yeah, so it's something like loop forever and loop. What does it do? It maybe does some actions which are non-critical. What do I mean by non-critical? These are the actions that do not affect the shared variables. Yeah, so only some local computation. Then, in order to have access to the critical section, so in order to have access basically to be able to change the shared variables, we first have to get the semaphore. So what are we going to do is we are waiting until the semaphore is free. The semaphore free in my case means Y is strictly larger than 0. Then what we're going to do, we're going to grab the semaphore, which means we're going to decrement Y by 1. That means now we hold, so P1 or Pi now holds the semaphore, and that means it has access to the critical section. So now we can do basically our modifications of the shared variables, and this is here symbolically given as the critical actions. So these can be several, can be a whole block of kind of assignments on the shared variables. And at some point, if you are done with, let's say, all the modifications of the shared variables, you free the semaphore, and free the semaphore means you increment Y by 1. Okay? Good. So in terms of a program graph, this looks as follows. We have three locations. One location that corresponds to the non-critical actions. One location that corresponds to this wait loop. So this is its wait I location. And one location that corresponds to being in the critical section. Okay? So I abstract from the exact modifications to the, let's say, local variables in the non-critical action. So this is an arrow. This is always enabled. So we start in the non-critical thing. Then it's always enabled, means true, and I did not indicate any concrete modifications of the local variables. I just want to stay here at the abstract level. Then we move to the location weight I, which corresponds to basically we are in this line of the pseudocode. Now we have to wait until y becomes 0, y is a positive. And that means you wait until the guard y is positive holds, and then we're going to decrement y by 1. Yeah. Now we are on the critical section or critical location, corresponding to being able to execute critical actions. And now we can, after we are done with this, we can release the semaphore, and that means we increment y by 1. So please, what you should take into account is that this location here is just indicated as one location, but in principle it could be that you are modifying many different local variables. That's all possible. Similarly here, it could be that you increment y by 1, but in the same time you also change several shared variables. Yeah, that's well possible. Good. So both programs are symmetric, so P1 and P2 have the same, let's say, scheme. So this is the scheme we have. We have two threads, P1 on the left and P2 on the right, and these are two program graphs. Now I would like to, let's say, model the parallel execution of these two program graphs. How can we do this? Well, this is just a scheme that we have just seen before. We are in this situation. What we're going to do is we're going to do the interleaving on the program graph level. This gives us, again, a program graph. And we're going to map this program graph to a transition system. And then we can see what are all the states, what are the possible values, for instance, of the semaphore, and so forth. So if I apply this scheme to this example, what we get is the following. Yeah, and this is just a Cartesian product. Yeah. So you take this graph, 3 locations, so we get 9 locations, 3 times 3. What we see, for instance, here, initially both threads starts in a non-critical section or non-critical location. Suppose we just look at the execution of one iteration of P1. This corresponds to this loop in the program graph. Yeah. Similarly, symmetrically, this is the loop of the second one. And now all kind of possible interleavings can take place. So for instance, in the state where, or in the location where this thread or this program is in weight 1 and the other one is in non-crit 2, then for instance, this one can also start to wait. That means you move from here to there. It's maybe hard to see, but this guard belongs to this transition, not to that one. Then you're in weight 1 and weight 2. Yeah, and now what we have to do, we have to either this one can go to crit 1 or that one can to crit 2, and that is guarded. So both transitions here are guarded with this guard and this action and so forth. Yeah. What is the critical location? The critical location is this one, because this states that both threads are in the critical section. And this is typically something you would like to avoid, right? Because that means that both threads can modify the shared variables at the same time. So in the program graph, this is reflected. Now the question, of course, is this possible? Yeah? Is this a true mutual exclusion algorithm in the sense that we can never reach a state in which both threads are having access to the shared variables? This you cannot answer easily on the program graph level, but therefore we're going to look at the transition system. So I'm going to tell you how we go from this program graph, this picture over here, to the transition system. And that are the idea here is that you then represent all possible states. Good, so here is, before I do this, here is a short example. So suppose that this one is in this location, weight 1. This corresponds to this parallel, let's say, composition of the program graphs to being in either of those composite locations. Now you can, for instance, this is reachable, and in order to reason about this, we have to look at the transition system. Here are some other examples, but I think it's hopefully clear. Here what you see is that if you move to that trajectory here, the first thread is in the waiting location, the second thread is in the critical section. Now we know that the variable y equals 0 because we have just basically passed this edge. In that edge y was positive, but y was decremented by 1, and that means y was 1 initially and now becomes 0, and that means that actually from here you cannot move here because the guard over here y is positive is no longer true, and therefore thread number 1 cannot access the critical section if thread number 2 is already in there. Good. So here is actually the reachable fragment of the transition system. So I only concentrate on those states that are reachable from the initial state. Remember, those two were the program graphs. I showed you the parallel composition before, and this is actually the transition system that corresponds to this parallel composition of the two program graphs. And now it is made explicit what are the values of y. Yeah? So what we see here is that, for instance, we start initially in non-crit 1, non-crit 2, the semaphore being available. Suppose that we move to the right. That means that thread 2 is moving to the wait 2 location, but the semaphore is still available. Now, for instance, we can move over here, non-crit 1, crit 2. That means in going from this state to that state, this thread has moved from this location to that location. That means it has grabbed the semaphore by decrementing it by 1. And that means if we move from this state, y is 1, to that state, you see that y becomes 0. Now maybe the first thread can start waiting, so that evolves into this location, that's okay, but there is no outgoing edge here that moves to crit 1, crit 2, because this is not reachable, because the current shared variable, this binary semaphore, is 0 here. And therefore this thread, which is in wait 1, cannot take this edge. This is simply disabled. Yeah. So by inspection, what we see on the basis of this transition system is that the state crit 1, crit 2 is not reachable. That means mutual exclusion is guaranteed. Any questions so far? No? Good. Okay, so here is a run of this program. So here you see that we can here go from non-crit to wait 1, non-crit to wait 2. That means that if you look at these two things, you see there is no access to shared variables. Yeah, in both this edge and that edge, you don't touch any shared variables, and that means you can adequately represent this by interleaving. And that's represented here by this yellow fragment of the transition system, which is the possible orderings of the two possible edges. What else do you see here? You see that you have wait 1 and wait 2. Now the situation is a bit different because they have basically access to the same shared variable. First and foremost, you need to check the value of the shared variable, and then you're going to modify it. Now the principle of interleaving, as we have seen already by means of a small example, is no longer straightforward applicable, and therefore you don't see this. And that means that this is modeled, if you have wait 1, wait 2, by this state in the parallel composition. And this is a kind of competition between the two processes. Both are waiting to get access to the shared variables. And because of the semaphore mechanism, if you have access, you first need access to the semaphore. Only one of them can access to the semaphore, and that's the whole principle. Good. Now this works for, this was a very simple mutual exclusion algorithm. I now would like to show you a somewhat harder example, which is known to be Peterson's algorithm. I will show it for two processes, but it works for arbitrarily many processes. That's also the strength of Peterson's algorithm. So the idea is that we have two processes, two threads, P1 and P2. They have their local variables, B1 and B2, and a shared variable x. So these are Booleans. X is either 1 or 2. So x is a kind of, basically think about this as a kind of variable that tells you who will get the next turn. It's either process 1 or it's process 2. Good. B1 and B2 are Boolean variables, but the critical point is you can read those variables from your other thread. You cannot modify them, but I can, as B1, as P1, can, for instance, have access to B2. So here's the protocol for P1. So it's again an infinite loop. You can do something non-critical, that's okay. Then you set the local variable B1 to 1, indicating I am number 1, I like to have access to the critical section, intuitively speaking. You set x to 2. giving the possibility that process 2 also has access to the critical section. Now you're going to wait until either x equals 1 or b2 is false. b2 is the local variable of p2. p1 cannot modify it, but can inspect the value. So it's read-only for p1. Now you enter the critical section, so you can modify some shared variables. And once you are done, what you do is you basically tell, I'm no longer interested in having access to the critical section, and the way to express this is by setting b1 to 0. Why is b1 setting to 0 important? Now think about the other thread. The other thread has a very similar guard as this, but then the second disjunct will be non-b1. Yeah, so by setting b1 to 0, it's a kind of a local signal to your competing thread saying, listen, maybe it's now your turn. So this is the program graph that models this behavior. Again, we have just 3 locations, non-crit, wait, and crit. If we evolve from non-crit to wait, that corresponds to executing those 2 assignments. That means in the program graph we have an edge labeled with the guard true, and with 2 assignments, b1 becomes 1 and x becomes 2. Yeah. But notice that here I deliberately did not have any in-between location. I do not only do first b1 to 1, then move to a location, and then do the assignment of 2 to x. No, I do both assignments by evolving from location non-crit 1 to wait 1. Then I'm in the await statement that corresponds to this guard. Basically, I do not take any action, so there are no actions here. Now I enter the critical section, which stands for this thing. And now I release, and release set means setting b1 to 0, which corresponds to this edge over here. Good. So what is important, as I already stressed, is that in this edge we take both assignments, and that means that if we are going to take the interleaving with the program graph of the other thread, those 2 assignments are atomic in the following sense. If this one has done the assignment to b1, it cannot be the case that before doing the assignment of 2 to x, that thread number 2 is doing a step. This is not possible. Yeah? This would have been possible if I would model it like this. If I would say something like non-crit 1, now I can do an edge, I say true, now I do the assignment b1 becomes 1, now I go to some in-between location, and then I do true, and then I do x becomes 2. Yeah. Here it is possible that this one does this one single assignment, namely the assignment to b1. Now maybe the other thread takes over control. Remember, we're modeling all possible orderings, so maybe the other one does an assignment locally to its own variables, maybe to b2, maybe to x, and only then this one can happen. Yeah? So this one is different than the one over there, and the way basically to represent this in terms of the program graph, and I try to make this explicit here, is by embracing those 2 assignments by means of an atomic statement. Really saying, take those 2 assignments and execute them atomically, which means don't allow somewhere in the middle, in particular here, that another thread is taking an action before you complete this whole block. Yeah? Good. So here is P1 and here is P2. P2 is similar, except that the guard here is x equals 2 or non-B1. That's the symmetric version to this one. We can build a program graph. It's exactly the same as before. It's just a parallel composition. So it's just a Cartesian product of the 2 program graphs. So similar picture as before. And we see here that in the program graph we have this, I would say, critical location where thread 1 and thread 2 are in the critical section. Good. So now what the question is this, for instance, reachable? No. And in order to answer this question, we are going to look at the transition system. So again, what is written down here on the bottom of the slide is the program graph of the multi-threaded version of those 2 threads of Peterson's algorithm. Now we're going to look at the transition system, and this transition system looks as follows. This is the reachable fragment of the transition system. There are more states, but they are not reachable, therefore not indicated. So here you see the transition system of Peterson's algorithm. First, what you see is there are two initial states. How is that possible? Well, I mean, we start here and we did not specify what is the initial value of x. Yeah, x could be either 1 or 2. It has not been fixed a priori what is the initial value, so we have to account for both possibilities. X being 1 or x being 2. So this is the version of x equals 2, that is x equals 1. For the rest, what you see, this is symmetric. Yeah? Good. Now what you also can see is that the value of B1 is actually given by weight 1 or crit 1, and similarly the value of B2 is given by weight 2 or crit 2. So why do I mention this? Now if you go back to the previous slide over here. So I like to model a transition system of this program graph. What are the states of these transition systems? Well, the states are the locations in this program graph. So these are pairs. So this is something of the form, for instance, crit 1, weight 2. What else do we have to store? Well, we have to store the values of all the variables. Which variables do we have? Well, we have a value for B1. So this has some value. B2 has a certain value. And X has a certain value, right? So states are actually quintuples. They have 5 different components, okay? Now if you look at my next slide, you don't see those 5 components, you only see 3. Yeah, and why is this? This is the fact because actually you can read the value of B1 and B2 from the other points. So B1 is given by weight 1 or crit 1. So if this is weight 1 or crit 1, B1 is 1, otherwise it's 0. Similarly for B2, B2 is equivalent to weight 2 or crit 2. So for the sake of shortness, I basically removed these two because the values of B1 and B2 are already given by the possible values of the first 2 components. Okay? So I reduced the quintuples to triples in order to make our life hopefully a little bit easier. So this means, for instance, that in the case weight 1, we know that B1 is true, and in the state non-crit 1, then B1 is false because this disjunction doesn't hold, and so forth. Good. So let's look at one scenario. Let's suppose that x initially is 2. So x initially is 2. Then we are in this initial state. The 2 program graphs are in non-critical section. X initially is 2. Now let's suppose that the first one starts to wait. This line corresponds to the second one starts to wait, but that's symmetric. So let's just pick that one starts first, which is weight number 1. That means that we evolve into this state. What does mean in terms of the program graph? Well, maybe we should take this program graph on the board. So this was the program graph for P1, right? We are non-critical. Then we can move here and we set B1 becomes 1 and X becomes 2. Now we are in the weight. This is 1, this is 1. Now we're in weight 1. Here we have X is 1 or not B2. Here we are in crit 1, and we can move back by saying B1 becomes 0. And here we start. Yeah, so this was the program graph for P1. So what we see here is that if we evolve from non-crit 1 to weight 1, which means we did take this edge, B1 becomes 1, but that's not explicitly represented because that was the component we already said, we missed. That's weight 1, and weight 1 is true, therefore B1 is true. And for the other case, X becomes 2, but X was already 2, so that's not, let's say, changing in this case. Okay, let's continue as follows. Let's suppose that now this program graph is in weight 1. It wants to enter the critical section. What do we need to check? We need to check whether, hey, this is strange, whether X equals 1 or not B2. Now X equals 2, so the first disjunct is false, right? but because of the second disjunct, not B2, right? And B2 is false. Why is B2 false? Because this is non-crit 2. That means this thing is false, and that means B2 is false, and therefore it's possible that the first thread enters the critical section. Yeah, this guard holds. What does it mean in terms of the local states? Well, nothing changes. There are no assignments here, so nothing is changing to X, right? But weight 1 becomes crit 1. This does not also affect B1 because B1 is weight 1 or crit 1. It was 1, it stays 1. Good. Now at some point we're going to release. So that corresponds to this edge over here. We're going to release the critical section that corresponds to this edge over here. We're going to set B1 to 0. And that means we move from crit 1 to non-crit 1. Because non-crit 1 becomes true, B1 becomes false. Yeah? Good. What else do you see? If process 1 is waiting, then also process 2 can start waiting. But now you see that the variable is changing from 2 to 1. Yeah, because if process 2 starts waiting, it performs the similar assignment like this. And it is a symmetric version that says x becomes 1. So you are here. And now both are waiting. Is it now possible that both can enter the critical section? No, because only the first one can enter. Because if you check at this scenario, x equals 1, so this disjunct is true. That means the first thread can enter the critical section. That happens here. The second one says x equals 2 or not B1. Yeah, but x is not 2, x is 1. And B1 is true, so therefore not B1 is false, and therefore the second thread cannot enter the critical section. Yeah. Despite the fact that they're both waiting, only process 1 can enter the critical section. So what we see from this transition system, there is no reachable state that says crit 1, crit 2. Good. There are many unreachable states which I did not depict on my slides. I only put the reachable states here. Good. This is what we just have seen. Now the symmetric version where both threads are waiting. Now the second thread gets into the critical section. That's the blue state. Then the second thread is going to release the critical section, and then we move up to the gray state and so forth. Now this first process can enter the critical section, so we move to the pink state and so forth. And this is the symmetric version. So now I would like to show you a variant of Peterson's algorithm, a slight variant, a very minor difference, and this is exactly the difference that I was already hinting at. Now I'm going to explicitly model this intermediate location. Okay, remember what was important? I took the 2 assignment and I said, okay, let's assume they're atomic. Let's now assume this is not the case. I'm going to show you that then things can go wrong. So I'm going to assume now a small modification. Rather than saying I have in one edge I do the assignment to x and b1, I now split them. And for the sake of this example, I decided to first do the assignment to x and then do the assignment to b1. Symmetrically, I do the same with thread number 2. I first do the assignment to x and then I do the assignment to the local variable b2. For the rest, the programs stay the same. So in terms of the program, what I do is I remove the brackets atomic. Yeah? Okay. So let's look at the possible execution. And in this possible execution, we're going to see that we can get that actually both threads are in the critical section at the same time, which is something we would like to avoid. So I start in this scenario, and now I indicated all state variables. So the first thread starts in non-crit 1, the second one in non-crit 2. Let's assume initially x is 1. B1 is false and B2 is false. Good. Now what can happen is, for instance, this thread can do the assignment to x. What does that mean? This does not change anything to x, but it moves from non-crit 2 to request 2. Now what we can see, the left thread is doing the same. It moves from non-crit 1 to request 1, so this becomes request 1, and now the value of x is changing from 1 to 2. This scenario was not possible in the previous program because of those atomic brackets. Now it is possible. The values of b1 and b2 did not change yet. Now let's move that the left thread is evolving. It sets B1 to 1. That's what you see here. And it evolves from request 1 to wait 1. The second thread did not do anything. Now it can enter the critical section. Why? Well, it has to check the guard. Is x equal 1 or not B2? Well, x is 2, so that's the first disjunct is false. But because of B2 being still false, it's possible, oh, here, B2 is false, it can enter the critical section. So now let's enter the critical section, and now you see already what's going on. This one can set now B2 to 1. That's moving B2 to 1. It moves from request 2 to wait 2. Now it's going to check this guard. Is x equals 2 or not B1? Yeah, x equals 2 is true. So it can enter the critical section, and both threads are in the critical section. Yeah? So you see just a small twist of this program, removing the atomic brackets and putting these assignments in this order. First doing the assignment to the global variable x and then doing something locally can make a bit of mess. Good. So if we build a transition system, I did not do that here because the program graph is already 4 times 4 locations is 16, and then you build a transition system, reachable states. If you would do this, or I would not do this by hand, if you automate this, then what you get is indeed that now the state crit 1, crit 2 is reachable. Yeah. And by means of model checking, this is something that you would like to be able to automatically check whether this is the case or not. Not by manual inspection, but in an algorithmic manner, of course. So this version is not correct. Not correct if you would like to have mutual exclusion. Yeah. Good. Okay. So this is what we just have seen. This is about this interleaving operator. Parallel composition, and on the program level, it's possible to communicate via shared variables. That's what we just have seen, and what you should keep in mind is that you describe the subsystems by program graph. One subsystem is one program graph, the second subsystem is a second program graph. Now you try to glue them together. When do you glue them together? You glue them together at the program graph level, and then you build a transition system. That's what we have seen today. The transition system, as we have seen last time, is basically obtained by unfolding. You look at all the possible locations, all the possible program values, and so forth. So now I would like to look at what they call synchronous message passing. And what we're going to do now is I'm going to introduce you an operator, which is now a double bar rather than a triple bar. And this operator is parameterized. And it's parameterized with a set syn. And syn is a set of actions. Yeah, and the idea is, the intuition is that this set syn is going to indicate which actions need to be executed synchronously by two transition systems. The actions that are not in this set are executed autonomously. Yeah, maybe a very simple example could illustrate this. Those people that have attended the lecture on concurrency theory in the last winter semester will here have at least an aha erlebnis, I hope, because this is also what I introduced there. So suppose we have, in this sense, two transition systems. A transition system 1 that has some initial state, then it can do, I don't know, an alpha, then it can move to this state, and then it can do a beta. Okay? Now I give you TS2. And TS2 can maybe do something like a gamma, then go to this state, and then do a beta. Yeah. And now what I'm interested in the parallel composition of the two transition systems. But as I was already hinting at that using the same names, I would like that those two threads synchronize over beta. Those alpha and gamma, they can execute autonomously, but they need to synchronize over beta. So the way I'm going to introduce this is this. I'm going to say this is a singleton set, beta. That's my example of this syn. And the intuition will be every action in this set need to be executed by the two transition systems simultaneously. Every action which is not in this set, they execute autonomously. There's no need for cooperation with the other partner. Yeah. Good. So if you label this by A, B, C, and this is maybe state 1, 2, 3. So what would you expect? Well, you expect something like a Cartesian product. So you expect that this thing starts in a state A1. And what can now happen? Well, I said alpha is not in this set, gamma is not in this set, so just apply interleaving. Yeah? So if we apply interleaving, you can do either an alpha or you can do a gamma. If we do an alpha, we go to B1. If we do a gamma, we go to A2. Now I can do a gamma in that state. I have moved to B, so now the current thing is here, I am in B, and this one is in 1, right? The dot meaning the current state of those two transition systems. What can happen? This one maybe wants to do a beta. But beta is in this set. It cannot do this beta on its own. It can only do this beta if its partner is ready to do this beta too. But that's not the case, right? Because the other one is still in 1. It's not able to do a beta here. It can only do a gamma. So we first have to do this gamma. So let's first do this gamma. So that means we do this gamma. Now we move to the state B2. And I hope you easily see that also if you do this alpha here, you get to the same state. No? This is symmetric. So now we are in this situation. This fret is here, that fret is there. And now both frets can do the beta because both are able to do them. So they shake hands, so to speak. And they evolve synchronously. And that means here there is one beta transition where both move synchronously. And that means this one moves here, that one moves there, and that means the state over here is the state C3. Okay, that's the principle. One thing that you immediately should observe is that this thing is the same as this thing with the empty set. Yeah? You never synchronize. Yeah? So what we have seen before is just a special case of what we have seen here. Good. Later I'm going to show you in the next lecture some things about channel systems, at least, unless time is still there. So let's call about synchronous message passing. So I have two transition systems, T1 and T2, and I have a set of synchronization actions. Okay? And typically I assume them to be a subset of the disjoint actions of both transition systems. And now what I would like to define, I would like to define a composite transition system, the parallel composition of T1 and T2, parallel with respect to this set sing. Same principle as before, we take the Cartesian product of the state space, S1 and S2. We take the union of the actions, and actually we're going to do the same with the atomic propositions and the labelings as we had seen before. The critical point is how to define this transition relation. Yeah? Good. So this works as follows. I have to distinguish two cases. The first case says, what happens if I take an action which is not in the synchronization set? So if you give me an alpha, which is in the set of actions of a process, let's say I being either 1 or 2, but not a synchronization action, these are the actions that a thread can do autonomously. No handshaking required. So what does that mean? Same rules as for interleaving. Nothing changes here. What is important, of course, is this premise here. Yeah? Only for those actions you do this. So here you see that if S1 can do an alpha and moves to S1 prime, according to the transition relation of the first transition system, then the pair S1, S2 can execute alpha and moves to S1 prime, S2. And the other rule is symmetric. The second case covers the case where we synchronize. So this is, in French, rendezvous or handshaking for all actions in the set sing. And then we evolve synchronously. What does that mean? If S1 can do an alpha according to its own transition relation and evolves into S1 prime, and if S2 can do this alpha according to its own transition relation and evolves to S2 prime, then they can jointly move by doing the alpha and move to the pair S1 prime, S2 prime. Any questions? Is this crystal clear? Okay, so I will give you another version of a mutual exclusion algorithm that now uses this handshake principle. And the idea is that we're going to add an arbiter. So we will have 2 threads plus a third one, the referee, the arbiter. What's the role of the arbiter? The arbiter is going to decide who is going to have access to the critical section. So this is the process. As before, it's an infinite loop. We do something non-critical, then we request, then we do something critical, and then we release, and non-critical. So the main change with what we have seen before, now I model this by means of actions, request and release. Yeah? So request is an action, I want to request access to the shed, to the critical section. Release means I'm going to release my privilege to have access to the critical section. So this is just a transition system. Transition system, not a program graph, it's a transition system, right? Why is it not a program graph? Because I'm talking about the parallel composition of 2 transition systems, right? It's not on the program graph level. And now we have an arbiter. The arbiter is a 2-state machine. It has 2 states, unlock and lock. Unlock means the shared variable is free, or the critical section is free. Lock means it's locked. This means that it synchronizes on the request. So here one of the threads does a request, and this request needs to be, as we're going to see, synchronized with the arbiter. So you can only do a request if the arbiter is also willing to shake hands and do the request. Then this one will move to lock, and the release is the same. You have to synchronize, this release has to synchronize with the release of the arbiter. Only if both threads agree on doing the release, in particular the arbiter does, and the arbiter makes sure that only one process has access to the critical section, and this arbiter is controlling who is getting access. So what we have is the following system. We have 2 threads. These threads as such do not communicate. Yeah? They are just modeled by means of this interleaving operation. Now they need to synchronize with one arbiter. Yeah. So this one can do a request, that one can do a request. They can do this independently. They don't need to synchronize over their own requests. But they need to synchronize with the arbiter. And the arbiter is going to pick one of them. Actually, non-deterministically, it's going to decide which process is going to have access to the critical section. Good, so this is what I just said. We have interleaving and we have handshaking. So this is a transition system of the threads. So what are the states? The states are triples, because we only have to keep track of the states of the individual transition systems. So we take the Cartesian product, as we just have seen. So we have things like non-crit 1, non-crit 2, unlock. Remember that this arbiter was a very simple machine. This arbiter was of the form, we were unlock, that is where we start. Then we can do something like a request. Then we are in the lock state. And then we can do a release. So what do you see here? Is that okay? Maybe first this one starts waiting. That's okay. And now it does a request. So for instance, this first process does a request. This can do this independently from the second one. It does not need to synchronize, but of course the request needs to be synchronized with this thing over here. Yeah. So maybe I draw this completely to make this more. Yeah, so if we have this, so here we have P1, or T1, I should say, T2, arbiter. Arbiter was this case unlock and lock. Request and release. And this T1 was a non-critical one. Now I can move to wait one. Now I can move to critical one. And here I have to do a request. And here I do have to do a release. And this was in parallel to this thing. And this whole thing was put in parallel, communicating over request and release with this transition system, right? So what you see is we start here. Now suppose that the left process starts waiting. It moves there. It can do this autonomously, right? There is some action here that I did not indicate, but it can execute this autonomously. Now it wants to request access to the critical section. Is this possible? Yes, this is possible. In order to do the request, he needs to synchronize with this process. This process is able to do the request. So this one moves to that state, that one moves to that state, and the first thread is in the critical section. Yeah. Now maybe the second thread starts waiting. It moves here. Is that process now able to access the critical section? In order to do that, it needs to do a request. It cannot do that on its own because it needs to synchronize according to this operation with the arbiter, but the arbiter is in a state where it cannot do a request. So this one is blocked. Unless the first thread releases, that can happen. It releases, it goes back. Is this possible? Well, let's check. This release means you need to synchronize. But this is in a state where it can do a release, so they move simultaneously. This one moves there, and that one moves here. And now the second thread can access the critical section. Good. Question for you, is this starvation freedom? Is it possible if I have two threads, they both want to access the critical section? Is it possible that one can starve forever? Yes. Yeah. It's modeling module exclusion, but it's maybe not starvation free. Yeah, because this arbiter can be very nasty and always grant access to thread number 1 and never get access to thread number 2. Or only finitely many times to thread number 1 and infinitely many times to thread number 2. Is this fair? Yeah, maybe not. Now, these are kind of things that we're going to discuss much later, or not much later, a couple of lectures later in more detail. Good. One thing that I would like to point out, so this is a special case that can happen. Both threads are waiting. How can this happen? Well, let's go back to the initial thing. This one starts waiting, moves here. It can do this autonomously. This one can start waiting. It does so autonomously. This one wants to do a request. That one wants to do a request. But they are both need to synchronize with the arbiter. The arbiter is a kind of a scarce resource. It can only do one request. Yeah? There are two partners that want to do a request. He can only grant one. Which one he or she is going to grant? Non-deterministically. Yeah? No coin flipping, no preference for 1 over 2. It's not the case that if number 1 has already a prime number of times have access to the critical section, then he prefers program 2. No, not of all of this. Just completely non-deterministic, selects number 1 or number 2. So this is reflected in this slide. Good. You can easily, let's say, generalize this for more than 2 processes. So suppose I have several transition systems and I would like to do something like this parallel composition. Then what you can do is something like this. You can define the composition of several threads. Now you have to define how to bracket this. I mean, this is not in general associative, especially not if sin is, this sin, if this differs from that sin, then it's no longer the case. So if you do this, we just assume, so that's the way we define it, that we first take the synchronization of these 2 threads, then we take the third one, then we take the fourth one, and so forth. So we take from left to right, bracket this, then you have an operation that works for several processes at the same time. Good. Anything else? So here I have a small example with 3. Actually, this is something What I do here is that there is a special case that sometimes is convenient. You just have a double bar. What does the double bar mean? You synchronize on all joint actions. Yeah? So you just assume all joint actions are synchronized. And that's used in this example. So there are 3 two-state transition systems, a scanner, a booking program, and a printer. And I'm considering the following. So the scanner can scan and then code. A booking program can code and price. A printer can price and print. The idea is that all common actions need to be synchronized. What does that mean? It means that you see that this one can do a scan. Is there somewhere else that can do a scan? No. So that scan can be done autonomously. But this code needs to be synchronized with the booking program, as well as the pricing of the booking program needs to synchronize with the pricing of the printer. The print itself can be done autonomously. So let's look what is the transition system. So this is the system I'm considering. So this is the transition system you get if you apply the definition. So what you see is that the states are, of course, triples, indicating every state of every individual transition system. So we start in 0, 0, 0. And now you can see what, for instance, happens. So, for instance, we start in this state. Okay, so this transition system starts in 0, that one, and that one as well. So we are here. Now, what can happen? Can this one do a coding? No, it cannot, because this coding needs to be done simultaneously with this coding, but the scanner is not in state 1, so coding is not possible. Similarly, pricing is not possible, printing is not possible, so the only thing which is possible is scanning. So that's what's going to happen, so we're going to scan. You see what happens, this one moves to that state over here. Now, this coding can happen because this one can move to 0, that one can move to 1. They do this simultaneously, so we go to that state. Now we can, for instance, scan the next, right? There's nothing against this, so this one can move here, for instance. I'm not sure what exactly, yeah, so this one is the scan that can happen here. But you can also do the pricing, which means that this one synchronizes with that one, and that means you move to that state. Yeah. In that state, you can still do the scanning, so you can move here. And in that state, you can still do the pricing. So here you see this diamond, which is again the interleaving. The interleaving now of scanning on the one hand side, and pricing that happens between the booking program and the printer. Good. And this is what you finally get. So here is another scenario. We first synchronize, then you do the coding, then you do the scanning, then you do the pricing, then you do the coding, and then you print, for instance, yeah, and so forth. Good. So what did we see today? We saw something relatively simple, namely interleaving, parallel composition, no communication. What was the caveat? The caveat is if we do this on program graphs, and program graphs may affect shared variables, the adequate way to do this is to first do the composition on the program graph level, then move to the transition system. What else did we learn? We saw a parallel composition operator where we can synchronize or not. So we have this handshaking principle. What I'm going to do in the next lecture, which is Friday morning, I'm going to introduce this notion of asynchronous communication, this mailbox principle. Someone puts a letter in your mailbox, sometime later you get it out. So it's not a synchronous handshaking, but it's a principle that is used very often actually in communication protocols. Again, the message will be the same. You can model this by transition systems. Good, thanks for today. Hope to see you back on Friday.